So good morning, everybody, first of all. My name is Mohamed Hosny, and I'm really honored to be with you today, especially that I have a lot of our respected colleagues and some of our professors, like Dr. Sabri, of course. So I would like to take this chance to thank you for your presence and, of course, to thank Dräger for the heroic effort that they performed to make this event true. And I would like to specify Mr. Mohamed Mutawakkil for all his efforts. Really, he did a great job. And the rest of the team, of course. Actually, we will start our day with low flow anesthesia. I know for the majority of you, you are experts. And I believe that it's to some extent an old and new at the same time topic. So we will just start with history about the low flow anesthesia. This is Joseph Priestley, and he is the one who invented oxygen in year 1774. So what is low flow anesthesia? Actually, with the start of the inhalation anesthesia in the middle of 18th century, the era of low flow was there, with the chloroform, which in that time they used to some extent semi-closed circuits. And later on, it was diminished when they start to use the halothane in the mid of 50s, because the first type of vaporizers used for halothane wasn't accurate enough to guarantee that the vaporizer is delivering what we require with the low flow of anesthesia, with the low flow circulation. Later on, in the 80s, with the invention of the isoflurane, and later on, after they start using the desflurane and sevoflurane, again, the use of low flow circulation of fresh gas flow start to rise again. But it was a problem regarding the definition of low flow anesthesia. So just let us make it an open discussion. What do you think about low flow? How you can define it? What's your opinion? There's any answer for this? Can you precise it by a number?
Sometimes below 1 liter per minute of fresh gas flow, or below 2, according to sources.
Why not 4? Why not 0.5? Actually, it was a matter of debate for a very long time. At the beginning, they said it should be less than the patient minute ventilation. So they defined it at the beginning, very early beginning, by less than 6 liters. By the time they developed this definition to less than 4 liters. Later on, they said between 3 and 4 liters. After this, they said 2 liters. Then less than 1 liter. And finally, they reached less than 0.5. So what's the right answer? After a lot of definitions, they reached the final definition of low flow anesthesia, which is less than 1.5 liter. Thank you very much. They reached finally the, after of course, I'm sorry. Yeah. So this was the history of defining the low flow anesthesia. And finally, they reach, we will discover in the next slide. But I would like also to define what's closed system anesthesia. And it's a low flow anesthesia in which the fresh gas flow uptake of anesthetic gases and oxygen by the patient and gas sampling the fresh gas flow do not exceed the patient metabolic rate and the gas sampling. Of course, all of you know that the patient metabolic rate average, the oxygen consumption in a patient who is 75 kgs is around 250, 255 milli, and the sampling is between 150 maximum to 200. So one of the definitions was it is just 0.4 mil per minute. We will go for just a further step to discover what's the new definition. Finally, low flow anesthesia. It is anesthesia delivered with fresh gas flow below 1.5 liter per minute, but maintaining slightly above the uptake of the patient. And the closed circle anesthesia is the anesthesia whereby fresh gas flow matches patient gases uptake and there is no excess gas leaving the circulation. And we can talk also about minimal flow anesthesia, which is below 0.5 liter per minute. And during our talk, we will discover that there is something called metabolic low flow, metabolic fresh gas flow, which reach around 0.3 liter per minute. Rebreathing describe a technique in which non-consumable gas will reroute in the circulation. We are classifying now the circuits to semi-open, in which the fresh gas flow is exceeding the minute ventilation. It's more than 6 liters. And semi-closed, in which the minute ventilation is higher than the fresh gas flow and it is higher than the uptake of the patient. And finally, the closed, in which the fresh gas flow equal exactly the uptake of the patient. So to some extent, I found during our previous discussions with our colleagues that there's a misconcept about closed circle anesthesia, because they are believing that closed circle, it means that it's the circle in which we can go below 1.5 liter. But actually, the true definition about closed circuit anesthesia is it is the circle in which we can reach up to 0.3 liters per minute. This is the diagram just showing us a very simple idea about the circle of the ventilation. So this is the source of the fresh gas flow. It will go to the patient during inspiration, and during expiration, it will come back again to the circuit. And there's a waste or exhaust site. This is another diagram showing us the idea of recirculation of anesthetic gas. So let us just refresh our basic knowledge about the circulation. During inhalational and manual or spontaneous breathing, the fresh gas flow will go to the patient lung and the expiratory valve is still closed and the excess of the gas will go out of the circuit through the ABL valve. During expiration, the expiratory valve will open and the exhaled gas will go out of the patient, filling the bag. If we will add a ventilator to this circuit, we will make the inhalational gas and the fresh gas flow circulate in this circuit. Of course, it's very primitive to say that lower fresh gas flow means higher rebreathing, and higher fresh gas flow equal zero rebreathing of gases inside the circuit. Is it clear here? Okay. So we will go a little bit also for the history to discover how they invented an equation to calculate the oxygen uptake by the patient, the nitrous oxide consumption by the patient, and the inhalational anesthetic agent uptake by the patient. This is the final that we know these days. This is the oxygen consumption by the patient. This is an example of isoflurane consumption by the patient in comparison to the time. It is milli per minute in comparison to the minutes. And finally, this is the consumption of nitrous oxide. Oxygen uptake equation was calculated by Professor Samuel Broadley. He actually worked in this very primitive laboratory. And of course, you can imagine how much effort he did to bring us the final equation of oxygen. And just to summarize it, this is the final equation how we can calculate the oxygen consumption by the patient. And then for the nitrous oxide, Professor John Severinghaus give us this equation. And from this equation, nowadays, we can say very simply that in a patient average of 75 kilograms, in the first minute, his uptake can reach up to 1,000 ml of nitrous oxide. And this uptake will be reduced after 2 hours more than 90%, and it will reach 90 ml per minute after 2 hours of anesthesia. And finally, the inhalational anesthesia equation was done by Lewis formula. And of course, you can see it's a very long equation and difficult. You can imagine how much the effort he performed to give us this equation. But thanks God that we can calculate everything easily now after the invention of this equation. This is just an example for different body weights and the uptake of oxygen, nitrous oxide, and sevoflurane with a concentration of 2% after 30 minutes. For the 75 kgs, the oxygen consumption will be around 255, 250 ml per minute. The nitrous oxide after 30 minutes will be around 130, and we don't need more than 12.1 ml of sevoflurane for the patient per minute after 30 minutes of anesthesia. Why we're talking about low flow anesthesia or minimal flow anesthesia or metabolic anesthesia? What do you think? Is it an important issue? Why, although it's a very old issue, we are repeating talking about it all the time? What do you think? What's the importance of it? Sorry?
Cost-wise.
Thank you very much, Dr. Tariq. This is the answer I'm hearing all the time.
Pollution.
Cost. Oh, thank you very much, sir. Actually, we were talking about it. I would like you just to think about that it is really beneficial for the patient, and this is our priority as anesthesia doctors and as physicians generally. Plus, we are saving our Mother Nature for the future generation. Finally, we are saving for wherever DHA or Ministry of Health or HAD or the owners of the hospitals. But actually, it is not the first reason, is only economical. So there's economical, environmental, and health care for our patient. And we will discover this. Yeah, this is one of the reasons. It's improving our care for the patient, and we will discover this actually. So there are medical reasons, economical reason, and ecological reason. For the medical reason, it will improve the climatization of inhalational anesthetics, and we mean by climatization, humidity and temperature. And also it increases mucociliary clearance, maintain body temperature, and reduce fluid loss. Of course, all of us know this equation that the soda lime will produce some heat. This is a study, it's actually an old study in 1994. It's not something new. It shows very clearly that with increase of the fresh gas flow, the humidity of anesthesia gas will be less. The less fresh gas flow, the humidity is more. And all of us knows that we need humidity for the fresh gas flow just to improve the ciliary function and to prevent complications in the lung. So increasing the humidity is something good. This is another study showing the temperature of breathing gases. And as you can see, if we will just reduce the temperature, the fresh gas flow from 1.5 liters to 0.6 liters, there's a statistically significant difference in the temperature of the fresh gas flow reaching the patient. This is a medical, another study showing us that the difference between the temperature, mean esophageal body temperature, between 0.5 liters and 5 liters. And you can see that the difference is significantly higher for 0.5 liters. The temperature is higher for the 0.5 liters. So reducing the fresh gas flow will improve the temperature of not only the body core temperature of the patient, but it will also give the chance for the gases reaches the patient to be more warm. Actually, this is a big study done data in CATO. CATO, of course, is a Dräger machine, and the result of this machine, the conclusion, showed us that the respiratory function and mucociliary clearance are better preserved in a low-flow anesthesia technique. It also, again, for the humidity, it showed us that the lower fresh gas flow, the better the humidity will be. And this is the temperature of inspired gases. And the conclusion is the reducing fresh gas flow during anesthesia led to more humidified anesthetic gases. Anesthetic gas temperature increased more rapidly, better mucociliary clearance, and it will improve the pulmonary function. The economical reason. Just can you imagine if we reduce the fresh gas flow from 3 liters to 1 liter per minute? How much anesthetic gas we can save? What's your expectation? If we would just reduce it from 3 liters to 1 liter?
1/3.
1/3, sir? It's roughly between 50 to 60%. Of course, with the climate of cost consideration, it's a big value. Actually, it's the big value. Again, it's not only the cost of anesthetic gas. It will be the cost of anesthetic gas plus the oxygen. So over 80% of our anesthetic gases are wasted when flow of 5 liters are used. We don't need this. We don't need just to throw our money to the ground. Several studies proved that reducing the fresh gas flow will have an economical impact. Typically, reduction of fresh gas flow from 3 liters to 1 liter will save about 50% of total consumption of any volatile gas. And as you can see, with the 1 liter for the sevoflurane, the cost is around $2.5, while it is around $5.50 with 3 liters. And for the sevoflurane or desflurane, the cost is even more. So this is what we are doing for our money. Just we are wasting it for oxygen-nitrous, inhalational gas, soda lime, and it is not necessary at all. Plus that we are harming our patient with the high flow anesthesia. So with the minimal flow anesthesia, we can go up to 0.5 liters per minute. And with the low flow anesthesia, we can go up to 1 liter. May I ask how many of you are using low flow anesthesia?
Since 10 years.
Wow, perfect. I'm really happy to hear this. So, sir, what you are doing? Tell us, I will be happy to know what's your own experience.
Yeah, we have the Drägers here since about 7, 8 years. So once we put the patient on, we start the anesthesia. Once everything settles down, we go down to metabolic flow very often with the auto control. And then we check the consumption of the gas regularly. So at very low flow, metabolic flow, it's around 7 liters per hour.
Perfect. So you are doing it automatically. It is not manual.
It's not by default.
Uh-huh.
We set it.
You set
It's
it.
there, we set it.
You set it, and you are keeping it automatically. Perfect. And what about the rest of our colleagues? Are you doing it automatically or manually? Manually. So.
Pediatric is difficult because sometimes you can't work with extreme low flow, but some devices have these options to go down, but if you have leakage, it doesn't work properly.
Yeah, perfect.
Sorry. There's a problem, you know, very often we use laryngeal mask in pediatric patient, we use uncuffed mask. So it's difficult with metabolic flow, we can't. We have to have a minimum flow of 1 liter to account for the leak. So that's why it's not by default. We put it, it goes by default, and we set the whole thing to account for the leak and everything.
Okay, so as you can, I'm really happy to know that the majority of you are using the low flow anesthesia, because still till the moment I'm facing some of our colleagues who are just debating the value of the low flow anesthesia, and I'm surprised to hear this. But the issue now is how we do it, because as you mentioned, there are different techniques. For example, the doctor is using the automatic technique while the doctor is using the manual technique. And should we use it from the first minute? Should we go for manual, then automatic? Should we use high flow, then low flow? We are going to discuss this in the following few slides. Of course, this is the ecological reason. All of us know that nitrous oxide is an ozone depleting and heat trapping greenhouse gas. And as you can see, it is one of the major ozone depleting gases after the CO2 all over the world. So I know that you will say, what I will do for the mother nature if I will just reduce my flow. But this is what we can do. This is what we can participate to save our motherland and our mother nature for the next generation. And this is the allowable, this is the maximum allowable biological concentration among the countries. This was published in 1979, but till the moment they didn't change this. In Germany, they are still allowing 100 particle per million for nitrous oxide, while in America they are allowing up to 50 particle per million for the nitrous oxide. And sure, sir.
Only as a feedback, N2O is eliminated in most of the hospitals. We don't use it anymore since many years, because we learned somehow, our management told, and the biomedical people, it's too expensive to maintain it. You know, you have many leakages, you lose a lot of these gases only technically before using it as a medical gas. So I think 10, 15 years ago in my hospital and in many other hospitals, we eliminated them totally. They are still available, you have these plugs, but they don't work. They are off.
Yeah, in some countries in the Middle East also, they eliminate using it for safety reasons, like what happened, I think in Egypt is eliminated. But it's not yet the routine all over Europe and USA. Yeah, of course. So this study was published in 1979, and it showed the lower the fresh gas flow, the less nitrous oxide particle per million. If we will go to 0.5 liters, we will be just 20 particle per million, while for 1.5, we are almost reaching 70 particle per million. So just can you imagine, with 1.5 liter, we will exceed the allowable upper limit in the United States of America. So this is what we used to do previously. Yesterday, we used to use high flow anesthesia higher than 2 liters, or low flow anesthesia, which is equivalent to around 1 liter. And today we are talking about 0.5 liters, or even metabolic rate, which reach 0.35 liters. But this is what our doctor said, that previously we used to use oxygen-nitrous. So how we are going to do it? As the doctor said, sometimes you are having leakage. So there are at least minimal accepted standards to perform low flow anesthesia. We should not go to low flow anesthesia if we don't have this standard. The circle breathing system with CO2 absorbers, and it should be very potent CO2 absorbers. And sometimes I noticed this with some cheap kinds of CO2 absorbers that really it will not work. And you will notice that the end tidal CO2 is rising all the time, even with 2 and 2.5 liters. So be sure that the CO2 absorber is functioning perfectly. The circle breathing system with CO2 absorbers, accurate flow meter for adjustment of fresh gas flow below 1 liters, gas tight breathing system. Breathing system should have minimal internal volume, and continuous gas monitoring must be employed, as our doctor mentioned, that we are keeping monitoring the gas all the time. What are the disadvantages of low flow anesthesia? Accumulation of unwanted gases into the breathing system. We may have any other kind of gas rather than oxygen, nitrous, and inhalational anesthetics. We may have it. Like what?
Helium.
Yeah, helium. CO2, it will be washed totally. And what else? What do you think, rather than helium? Any other more significant gases? Carbon monoxide toxicity?
I said CO.
Yeah, I hear it CO2. Sorry, sir. Oh my God, I'm really sorry. I apologize for this. I thought it's CO2. Sorry. Acetone. So this is the disadvantage of using low flow anesthesia with such type of patient. So accumulation of unwanted gases, and we will see later on what are these unwanted gases. If you put little gas into the breathing system, little or none will come out. As a result of this, failure to flush gases out of the system may introduce which are not taken up by the patient or absorber. Okay, so these are the problems. We can't use the low flow anesthesia with alcohol intoxicated patient, with a patient with carbon monoxide toxicity, or with diabetic patient. Therefore, there is a limitation of using low flow anesthesia with this type of patient. But I don't believe that these patients exceed 0.5% of what we are seeing per year. Do you agree? Argon, hydrogen, nitrogen, acetone, carbon monoxide. Concerned about safety in low flow anesthesia, you have to keep this in mind all the time. Guard against hypoxia, the gas volume deficiency, missed doses of volatile anesthetic, exhaustion of absorbent. So how we are doing it clinically? Delivery of low flow anesthesia. We have one of 3 options, either to do it oxygen with nitrous, or oxygen with air, or 100% oxygen. We will just start with delivery of low flow anesthesia, initial high flow, low flow, and recovery. This if we are going to do it manually. Because again, it was a matter of debate, and I found some of our colleagues starting low flow anesthesia from the first minute. They are starting low flow from the first minute. And you can do it manually from the first minute and after intubation. It's impossible to reach the desired end tidal volatile anesthetic from first minute manually. You can do it automatically by the automatic gas control or target controlled inhalation anesthesia, whatever the name of this technique you are using in the machine. But some of our colleagues are, after insertion the tube, they are just opening the fresh gas flow 0.5 and 0.6 from the first minute. And I think they will never reach the target, whatever they will do. So initial high flow, of course, we have to go for sufficient denitrogenation by pre-oxygenation, and we have to do the pre-oxygenation with at least 5 liters and above, from 5 to 6 liters. 100% oxygen. We will let the patient to breathe for 3 to 4 minutes, aiming 100% denitrogenation. To wash off the wanted nitrous oxide in the anesthesia, establish the wanted concentration of volatile anesthetic, stabilization the anesthesia circuit system, filling the reservoir back. So at the beginning, we will go with the oxygen, 5 liters, aiming to decrease the nitrogen. And after 3 minutes, we will start the anesthetic gas. After the 3 minutes, and after intubation, or if we will go for inhalational anesthesia, but it's not preferable to go for inhalational anesthesia with low flow because you can guarantee 100% there is a leakage. After 3 minutes, we will reduce the flow from 5 liters, 100% oxygen, and we will make it whatever, 40 to 60% nitrous oxide or air, or 50-50. 1.5 liter for oxygen and 3 liters for nitrogen. This is the high flow. And after 10 minutes, we will reduce it to the low flow. I'm talking about the manual technique. After high flow phase, preset time, or when the target gas concentration has been achieved, can be reduced, the fresh gas flow can be reduced to the desired level. So we will start talking about oxygen-nitrous volatile anesthetic. We will start inhalational high flow phase for 10 minutes. And the high flow phase, as we mentioned, we can go up to 4.5 or 5 liters. With the isoflurane concentration, increase this numbers for the high flow. Reduce this number for the high flow by 40 to 50%. So for the isoflurane, we are going to use 1.2. For the sevoflurane, we are going to use almost 1.8 to 2. For the desflurane, we are going to use around 6% with the high fresh gas flow, which is around 5 liters for the first 10 minutes. Then, after the 10 minutes, after stabilization of everything, after we reached the wanted concentration of entitled volatile anesthetic, we reduce the flow to 1 liter, which is going to be 0.5 to 0.4 oxygen and 0.5 to 0.6 nitrous. And we will increase the isoflurane to 2% or sevoflurane to 3% and desflurane to 8%. At the recovery phase, we usually close the vaporizer 10 minutes before the end of the surgery, and we increase again at the end of the surgery the fresh gas flow up to 4.5 or 5 liters. For the oxygen, air, and volatile anesthetics, we start the initial high flow phase for 10 minutes, 3 liters for air, 1 liter for oxygen, and we start with 2.5% isoflurane or 3.5% sevoflurane or 6% desflurane. And after the 10 minutes, we will reduce the flow up to 0.5 liter, but we have to increase the anesthetic around, as you can see, 50%. So we increased, I'm talking about the manual technique. It is much more difficult to perform it manually. You have to do a lot of work when you are doing it manually. So we have to increase the isoflurane to 5% or the sevoflurane 5% and the desflurane 8%. If we are going to do it low flow anesthesia oxygen mixture for the recovery, it's the same. We can close the vaporizer 10 minutes before the end of the surgery and increase the flow again to 4 or 5 liters. And now, anesthesia with nearly closed system, in which we can go for the metabolic rate. Initial high flow, it is the same. And when we will reduce the flow to 0.3, we have to keep the percent of volatile anesthetic a little bit higher, 5, 8, and 10%. So should we use 100% oxygen or oxygen with air? It's actually, again, a matter of debate for the last 6 years. We grew up with the concept of 100% oxygen is hazardous for the patient. But in the last 8 years, there is a lot of debates regarding this point because they discovered a lot of advantages for the oxygen 100% during anesthesia if the surgery time is less than 6 hours. And of course, with limitation to some extent. So it will improve the wound infection rate, it will decrease the post-operative nausea and vomiting, no relative atelectasis happen within the first 6 to 8 hours, it is safe during hypoventilation, less periods of hypoxia, very easy inhalational anesthetic technique, whatever you are going to use. But, and even the ERAS, the Enhanced Recovery After Surgery guidelines are supporting use of 100% oxygen. I'm not saying it's the best, because again, there are a lot of disadvantages still. It's a matter of debate for using 100% oxygen, especially in neonates, of course, and in COPD patient, and in laser surgery. How do you know you have a stable inspired oxygen volatile concentration? Just believe what you are measuring. You have to just watch all the time the FiO2, expired concentration, the peak pressure, the end tidal CO2. And these are just words from different countries and different doctors. From Finland, they are supporting using it, fresh gas flow between 0.5 and 1.5. And US, they are using it with the same range. In Norway, it is almost mandatory. In Canada, they are using around 1 liter. In United Kingdom, there is a very strict approach for the gas economy. And thank you very much.